It's been good. Yeah, a lot of meetings today. There's been a lot of meetings this week in general. It's like kind of been make up for the spring break, but yeah, doing good. How about you? How's your day going? Oh, nice. Where are you? Where are you interviewing at? Awesome. Nice. Oh, best of luck with the interview. Yes. Yeah. So we're gonna have our midterm in 2 weeks. Mm-hmm. Yeah, it'll be same format as the other midterm. So same number of questions, same format. So 3 conceptual questions and 2 problem solving questions. Yep. And I'll do a midterm review next week as well. All right, it's 2:30, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today? Doing good, I hope. Yeah, it's good. Yeah, it's our second class after the midterm, after the spring break, sorry. And so, hopefully, things are getting back into the swing of things. All right, and so for our class, what the plan for today is we're going to finish up our lecture notes on free convection, and then we're going to start our next set of lecture notes on heat exchangers. So I expect it'll be kind of half and half for both set of lecture notes today, okay? Homework 5, and so homework 5 is going to be due on Monday. And then just to give you guys some more practice for heat exchangers before the midterm, there's going to be another homework assignment that's going to be assigned next Monday as well, right? So homework 5 due on Monday, homework 6 will be assigned on there as well, okay? And just like what was mentioned before the class, we have our second midterm. It's coming up relatively soon, so it's going to be in 2 weeks. Right? So not next week, but the week after that. And so in terms of format, it's going to be the basically the exact same as the first midterm. And so we're going to have 3 conceptual questions and 2 problem-solving questions. I'm going to post a study guide, and I'm going to do a review as well. Okay, and so all that's going to take place on next week. So so definitely keep an eye out for that. Okay. All right. So are there any questions before we get started for today?
You said the test was 19?
Yeah,
Turning out?
Yeah, on the 21st. Yes.
Okay. I thought you said next week.
Yeah, so not next week, but the week after that. So 2 weeks. 2 weeks from today. That's going to be our second midterm. Okay. All right. So if there's no more questions, let's go ahead and get started. And what we left off on Monday was learning about free convection. All right, so just a little bit of a refresher. Remember, free convection is basically convection heat transfer that occurs when you don't have any kind of external forced flow. And the main way that we get this free convection is through density differences within the fluid. Okay. And so what we can say is that fluid flow happens naturally, or I guess as naturally as it can. Okay, so I'll put naturally maybe in quotes, through density differences in the fluid. And the way that we obtain those density differences is through differences in temperature, right? Because we know that as a fluid either heats up or cools down, or its temperature changes, then its density is going to change as well, right? And so that density is something that's very, very specific, or very dependent on the temperature. Okay? And so we've gone over kind of in pretty good detail about cases with vertical plates, right? And so basically where the flow is kind of parallel to the plate. Okay. And so I think what we left off on is, free convection for horizontal plates. Okay. And the thing that's unique about these situations is that, depending on the temperature of the plate and depending on, whether we have fluid above or below it, we can either have fluid that goes towards the plate or we have fluid that goes away from the plate. Okay. And so, basically the way we can sum that up is our Nusselt number correlations depend on whether the fluid's going towards or away from the plate. Okay. And so last time we went over these two situations here. So let's say that we have a situation of a hot plate, right? Okay. And so the hot plate is going to heat the fluid up, and so it's going to want to make the fluid rise, right? And so if the fluid's going to rise, then if the fluid's coming at it from the bottom, then the fluid's going to come towards the plate, right? Okay. And so if you have a hot plate on top of some cooler fluid, then the fluid's going to want to come up and go towards the plate. Okay. Whereas if you have a hot plate at the bottom of a bunch of fluid, that's going to want to make the fluid go away from the plate because it's only going to want to make the fluid rise. Okay. And then the opposite is true for a cold plate. So a cold plate is going to want to make the fluid drop down. Okay. Right. And so for a cold plate, the fluid on top is going to want to go towards the plate. Where the fluid on the bottom is want to go away from the plate. Okay. Right. And so when you're doing these problems, it's always good to to know whether your fluid's going either towards the plate or away. And what you'll see on the next page is that this affects the equations that we're going to use for our Nusselt number. Okay. All right. So any questions on this so far? This is kind of just a recap of what we did last time. Okay. All right. And so here are the Nusselt number correlations for these situations. And so what you'll see is that these Nusselt correlations, they don't really care about whether your plate is hot or cold. All it really cares about is if the fluid is either going towards the plate or away. And the reason for that is, these are kind of the primary ways that the fluid flow patterns are going to be affected. Okay. All right, so let's go towards the plate first. So if your fluid is going towards the plate, our Nusselt number correlation is given by the following. So our Nusselt number is going to be equal to 0.52 times the Rayleigh number with respect to L to the 1/5 power. Okay. And this is valid for if the Rayleigh number is between 10 to the 4th and 10 to the 9th. Okay. Okay. And so, if you have, the Rayleigh number between these two, which is a pretty large range. So you're talking about anywhere between 10,000 and a billion, basically. And so this is, then you're going to be fine. Okay. All right. So now let's look at the Nusselt number correlation for going away from the plate. All right, so we have two here, and the two here are going to depend on different regimes of Rayleigh number. And so the first one is going to be 0.54 times the Rayleigh number raised to the 1/4 power. And this is going to be valid for the following range. And so it's going to be valid for if your Rayleigh numbers are between 10 to the 4th and 10 to the 7th. Okay. And so a slightly smaller range here, but you'll see we have one more to kind of cover all the rest of the stuff. Okay. All right. And so also in this category of going away from the plate, we have another Nusselt number correlation. All right. And so this Nusselt number correlation is going to be 0.15 Rayleigh number to the 1/3 power. Okay. And it's going to be valid for kind of the upper half of the Rayleigh number regime. And so this is going to be 10 to the 7th, which is less than Rayleigh number, which is less than 10 to the 11th. Okay. Right. And so it's not quite laminar and turbulent, but you can almost think of these as having, one Rayleigh number for kind of the, or one Nusselt number correlation for, relatively low numbers of Rayleigh. And that's going to be, like our laminar one. And then the second one here, that's going to be for higher Rayleigh numbers, which is kind of like the same as turbulent flow. It's not quite that, because the trigger for turbulence for free convection is Rayleigh numbers equal to, or I should say the Grashof number is equal to 10 to the 9th. But, it's kind of the same idea here. Okay. One other important thing to note is that, whenever you're computing the Rayleigh number or the Grashof number, you need to plug in a length L, right? But for horizontal plates, our situation is a bit unique because our flow is going basically perpendicular to our plate. And believe it or not, this is unique because up until this point, we've only considered cases where the fluid flow is parallel to the plate. So it's going kind of in the same direction as the length of the plate. Here we have kind of the opposite situation where, the flow is either going perpendicularly towards the plate or perpendicularly away from the plate, right? And so we have to be really careful with the length that we plug in here because it's not just going to be the length of the plate. Right? And so here we're going to plug in basically almost kind of the same thing as like the characteristic length. And so if you kind of remember from our unit on lump capacitance, the way that we computed the length there was we took the ratio of the volume and the surface area. And so here it's going to be fairly similar, but we don't have a volume here because we have just a 2D plate. And so the length that you plug in is going to be a ratio of the surface area to the perimeter of the plate. And so, make sure you plug in the appropriate length here because it's very easy to kind of make the mistake not to. Because what you don't want to do is you don't want to take, the horizontal length of this plate right here, right? You don't want to plug that one into the Rayleigh number formula because that's not the direction that the flow is going. The flow is going perpendicular to that, right? And so you want to plug in kind of a characteristic length scale that's kind of associated with that kind of perpendicular direction. And this, ratio of the surface area to the perimeter, is kind of gives us exactly that. Okay, so any questions on this before we do an example with this stuff? Okay, right, so let's go ahead and do an example. And this is a nice example because it kind of combines kind of everything that we've done for free convection. Right? And so here, let's consider a rectangular duct filled with stagnant air. Okay. And so this could be a duct that that you might see in like your air conditioning system or any kind of ventilation system out there. Okay? And so the duct looks like this. Okay, so it's rectangular in shape. And so the length of this guy will be 0.75 meters. The height is going to be 0.3 meters. Okay. And so that's the cross section. And then the surface area of this duct, or the surface temperature, I should say. The surface temperature here is going to be 45 degrees C, right? So fairly warm. And then the air on the inside will have a temperature of 15 degrees C. Okay. Right, and so we have basically a hot surface and a cool fluid. So that's kind of the straight on view of this duct. And then if you draw kind of the 3D view, kind of looks something like this. Where we're going to assume that this length right here going into the page, and so I'll call this W. And so this W here will be 1 meter. Okay? So we're going to go 1 meter basically into the page. Okay. All right. And so in this case, since we have stagnant air, we're not going to have any kind of forced convection. And so we're just going to, the only convection that we're going to have here is free convection. Right? And so this problem, what it's asking us to do is it wants us to determine the rate of heat loss from this duct to the air. And so to do that, we're going to need our convection coefficients, okay? And then we're going to find those using free convection. Right? Okay. And so let's go ahead and run through our usual convection solving methodology here, and then we'll go ahead and solve it that way. Okay. Because the first thing we're going to need is we're going to need our values of H. Okay. And I say plural values of H because here we have kind of a complex, relatively complex situation. But if we kind of break this up into each of the different sides of the duct, then what you'll see is that we actually do have all the tools that we need to solve this. All right. And so the first step of our process, remember, is always going to be identify the situation. And here it's actually pretty relevant because it's not just a straightforward plate, in a stagnant fluid. Okay. All right. And so let's go ahead and identify this. So, we have a rectangular duct here. So we have kind of a rectangular shape, but we don't really have any theory that kind of goes along with this, at least not in free convection, right? And so we never learned any free convection for for a horizontal duct. Okay? But what we can do is we can take this horizontal, or we can take this this rectangular duct here, and then we can break it up into different surfaces, right? So let me go ahead and do this. So let me go ahead and circle these guys in red. Okay. And so in red right here, these are basically the same as vertical plates, right? Okay. All right, so that's great because we know how to do vertical plate free convection, and so we can just go ahead and use our theory for that. Okay. Right, so next I'm going to circle the top surface in blue right there, and so that top surface is basically the same as a horizontal plate, right? But remember, for horizontal plates, we need to know whether the fluid is going to go towards the plate or away from a plate, or away from it. Okay. And so since this, duct right here has a higher temperature than the fluid, we know that it's going to cause the fluid to want to rise. Okay. And so we have a hot plate on top of some fluid. And so what this tells us is that, we're going to have fluid that goes towards the plate. Okay. And then the last surface on this duct here is, of course, the bottom one. And the bottom one, we have an opposite situation where we have a horizontal plate, but the fluid is going to go away from it. Okay. And so with all of these with all these situations identified, we'll be able to compute the Nusselt number correlations for each of them, because now we've identified, our three different situations here. Okay, so we have two vertical plates, one horizontal plate where the fluid's going towards it, and then one horizontal plate where the fluid's going away. Okay. All right, and so now that we have this, we can go ahead and start computing the properties. Start computing the Rayleigh numbers, and then finishing up the problem. All right, any questions on this example so far? Okay. All right, so let's go ahead and start and continue on with our process. Right? And so our second step in the process is always going to be to specify the reference temperature and evaluate the fluid properties. And so the reference temperature is basically the same as our film temperature here, right? So we have TF, which is our film temperature. We're just going to take the average of the two temperatures, right? And so we take the average of this. This is 30 degrees C, which is the same thing as 303 Kelvin. Right? And so from here, we can go ahead and look up all the properties of air at this temperature. All right. And so if we look up the properties, you can either use table 8.4 in the book, or you can use some kind of online calculator or online material data sheet. Okay. And we end up with the following. Okay. And so we have the viscosity first. So this is kinematic viscosity. And so this is equal to 16.2 times 10 to the minus 6 meters squared per second. Okay. Next, we have beta, which is our thermal expansion coefficient. Right? So 0.0033 K minus 1. Right? Next, we have our thermal conductivity. And so our thermal conductivity is 0.0265 watts per meter K. Right? And then we have our Prandtl number. Our Prandtl number here is 0.71. Right? All right. And so that's all the fluid properties evaluated at the appropriate temperature. Okay. And so step 3 now is to compute the Rayleigh number, and then determine whether the flow is, or determine which Nusselt number correlation that we're going to use. Right. And so we're going to need to do this separately for the horizontal and vertical plates, because each of them are going to have a different length that's associated with them. Okay. All right, so first let's do it for the vertical plate. And so for the vertical plate, since the flow is going to be just kind of right parallel to that plate, we can just use the length of that plate. Okay. All right, so let's go ahead and compute the Rayleigh number. And so the Rayleigh number for the vertical plate, we can just go ahead and plug everything into this equation. And so we have G times beta times Ts minus T infinity times H cubed divided by nu squared times the Prandtl number. Okay. And so we go ahead and plug everything in here. And then what we get from this is 7.07 times 10 to the 7. And so this, for a vertical plate, since this is less than 10 to the 9th, this is going to be laminar flow. Okay. And so that'll tell us, which Nusselt number correlation we're going to use. And so it's going to be the one with the Rayleigh number raised to the 1/4 power. Okay. All right. Any questions on this so far?
Professor, how do you know to use the vertical length? I mean, the length of the plate for the vertical plate?
Right. And so that's always going to be the length that you use for vertical ones, because remember for free convection, your flow is either going to go up or down, because everything here is buoyancy driven. And so we have the flow that kind of goes like this, right? And so since that flow is going in that direction, we want to compute the length in that direction. And so that length is going to be h, which is 0.3 meters. Yep. All right. Any other questions before we do the top and bottom plates? Okay. All right. And so the top and bottom plates here, these are horizontal plates. And so the length that we compute has to be based on the ratio of area and perimeter. Okay. And so we have L is going to be equal to area, surface area divided by perimeter. Okay. All right. And so how do we actually compute these? And so, if we look at the vertical plates, the horizontal plates here, the horizontal parts have a length in one direction of 0.75 meters, right? And if you can kind of use your imagination to see that, these horizontal plates are going to extend into the page, right? So it's basically going to be this top surface here that I'm highlighting is going to be one of them, right? And so the other dimension for that horizontal plate is going to be the width into the page, which is 1 meter. And so the schematic for those horizontal plates would look like the following. And so in this direction, we have 0.75 meters. And in this direction, we have 1 meter. Okay. And so from this, we can say that the surface area of this plate is just going to be the product of these two dimensions. So it's going to be 0.15 times 1. Okay, so it's going to be 0.5 meters squared. And the perimeter here is just going to be the sum of all the dimensions here. And so we have 0.75 meters plus 1 meter plus 0.75 meters plus 1 meter. Okay. And this is equal to 3.5 meters. Right. And so the length here is just going to be the ratio between these two. So it's going to be 0.75 meters squared divided by 3.5 meters. Okay. And then what we get from that is 0.214 meters. Okay. And so now we can take this length and then plug it in to solve for the Rayleigh number. All right. And so both the top and the bottom plate are going to share the same Rayleigh number because they're, they have the same, dimensions and everything. Okay. And so the Rayleigh number is going to be G times beta times Ts minus T infinity. Okay. Multiplied by this length squared. And so it's going to be, or this length cubed, sorry, 0.214 meters cubed divided by viscosity squared. Right. And so now we can plug everything in here. And then what we get from this is 3.64 times 10 to the 7th. Right. And so now that we have the Rayleigh numbers for both the vertical plates and the horizontal plates, we're ready to compute Nusselt numbers using the appropriate correlations. Okay.
Professor,
Yep. What's up?
do you think you can go like the reason why you find L for a horizontal plate again?
Yeah. So for horizontal plates, the reason we use this formula for L, the reason we do that is because the flow isn't going parallel to that plate, right? And so actually, let me draw this on the next page here. Because remember, whenever you have flow that's driven by buoyancy forces, the flow either has to go up or down because that's just the way the gravity field is. And so if you have a vertical plate, right, and you have flow that's either going up or down, right, this flow direction is parallel to the plate, and so it's going the same direction. And so we can just take this length of the plate here, and that's the length that we need for to plug in for the Rayleigh number. But for a horizontal plate, a horizontal plate is just by definition going from left to right, basically, right? And so the flow here isn't going parallel to the plate; it's actually going perpendicular. So it's going up or down. And so let's say that it's either going like this, right? And so the length that we plug in for the Rayleigh number, it has to be some length that's associated with the flow direction. And this is true even for the Reynolds number too. And so for the Reynolds number, there's usually the length that you plug in has to do with the flow direction in some kind. Usually. And so kind of the notable exception for this is internal flows where we use the diameter of the pipe, even though the flow is going, into the pipe that way. But that's kind of an exception. That's not really the rule. And so in this case, since the flow is going up here, we have to come up with a some kind of characteristic length. Okay. And so this is kind of the same as when we were looking at Biot numbers, right? And so when we were computing Biot numbers and we had, some kind of awkward looking shape, like, I think before we did Biot numbers with like either a rod or a sphere, but if you want to compute the Biot number of like a garden gnome or something like that, it doesn't really have like a good dimension that you can use for that. And so the way that we computed the length to plug in for the Biot number was we took the ratio of the volume of the object over the surface area, right? And so this is kind of the same thing. And so, because we have kind of a shape that, in a broad sense is simple because it's just a horizontal plate. But for the flow, it's more complex because we have flow going perpendicular to it. We have to come up with a characteristic length formula in order to compute that. And for these situations, the way that we can do that is we take the ratio of the area, surface area, and the perimeter. And so this length right here, this is a better metric or a better length to plug in for the Rayleigh number versus this length right here. Right? And so this length, we'll call it LH. Right? This LH is not a good indicator to use for the Rayleigh for the Rayleigh number because it goes it's perpendicular to the flow. And so we want one that's kind of more indicative of kind of this direction right here. And by taking the surface area to perimeter ratio, that's a little bit better of an indication in that direction. Yeah. Mm-hmm. Does that make it a little bit more sense why we do this?
Yeah, thank you.
Great. Mm-hmm. Okay. And so now that we have the Rayleigh numbers, we can go ahead and move on to the next step in the problem, which is computing the Nusselt numbers. All right. And so we're going to do, 3 different situations here. And so first we're going to do the vertical plates. All right. And so the vertical plates for laminar flow, right? Because our Rayleigh number was less than 10 to the 9th, right? And so our Nusselt number in this case is going to be 0.59. Rayleigh number to the 1/4. Okay. And this Nusselt number is going to be 54.1. Okay. All right, and so now let's do the top plate. Okay. And for the top plate, because we have a hot plate here, the fluid is going to go towards it. And so we look into our Rayleigh or our Nusselt number correlations, and if we have fluid that's going towards the plate, then we have a Nusselt number correlation of 0.52, Rayleigh number to the 1/5 power. Okay. And if we plug this in, this gives us 16.91. Next, we have the bottom plate where we have flow that's going away from it. Okay. Right. It's going away, and our Rayleigh number is greater than 10 to the 7th. Okay. And so we're going to use the correlation for that. And so this is going to be 0.15. Rayleigh number to the 1/3. Right. And this is equal to 49.71. Okay. And now that we have the Nusselt numbers, we can go ahead and compute the convection coefficients.
How do you know it's towards or away again?
Right.
For both those, for the top and bottom plate?
Yeah. And so for both of these cases, we say that the entire duct surface here is at 45 degrees C. And so if we compare that to the air temperature here is only 15 degrees C. And so in both cases, we have basically a hot plate or a hot surface in a cold fluid. Right? And so, in this case, since we have the duct that's heating up the fluid, it's going to want to make the fluid rise up because it's going to make the density lower, and it's going to want to make it go up from buoyancy forces. And so if the fluid's going upwards, then we know that the top plate, the fluid's going to go towards it, right? Because it's going up towards the top one. And then for the bottom plate, the fluid's going to go away from it because it's going to go from the bottom. It's going to go upwards like that. Yeah. And so the way you determine whether the fluid's going towards or away from it is you look at the relative temperatures between the surface and the fluid, and you see, which direction does the fluid want to go, either up or down, and then you see if that's either going towards or away from your plate. Yeah. All right, question. So for vertical.
Okay. Yeah, that makes.
Oh,
I was gonna say, I think that makes sense. I think I was just imagining it as if it was like a section and air is flowing outside of the duct and then over it instead of just purely inside.
Ah,
'Cause, like,
yes.
the word filled changes the problem completely.
Ah, yes, yeah. So for this case, we're looking at the flow or the air inside the duct purely. On the outside, you of course I think you'd have convection, heat transfer there as well, but we're neglecting that for now, just because we're not sure what the condition outside of the duct is. Yeah. Mhm. All right, question. So for the vertical plates, is that Newton number for both the plates or just one of them? So it's going to be for both of them. Yeah, so that's a great question. So both the vertical plates here are identical, and so that Newton number is going to apply to both of them. Yeah. And so what you'll see later, what you'll see in a bit, is that after we compute the convection coefficients, we're just going to, and we compute the heat transfer, we're just going to multiply that by 2 for both of the vertical plates. Yeah. Mm-hmm. Okay. Convection coefficients. All right. And so now let's take our Newton numbers here and then let's compute the convection coefficients. Right. And so for the vertical plate, we have H, and this is equal to Kf divided by H times the Newton number. Let me call this Newton number 1, just to kind of differentiate them. Okay. And so this is equal to 4.78 watts per meter square K. Okay. And so for the top plate, we'll call this Newton number 2. Okay. And so H2 is going to be Kf divided by Lc, where that Lc is that length that we computed on this previous page that we got from the ratio of the surface area and perimeter. Okay. And so it's going to be Kf over Lc times Newton number 2. And so this is going to be, let's see, 6.16 watts per meter square K. Okay. And then finally, we have the bottom plate here. And so for the bottom plate, we'll call this Newton number 3. And this is equal to Kf divided by Lc times Newton number 3. Okay. And we plug that in, and what we get is 2.09 watts per meter squared. Okay. I think I have a typo here. I think these two should be reversed here. And so I think because the bottom one has a higher Newton number, and so that should have a higher convection coefficient. And so let me go ahead and swap these. And so this should be 2.09, and this one should be 6.16. All right. So I apologize for the confusion, but yeah, I think there's a typo in my notes. But in the end, we're going to compute the same thing, but just so that we're keeping things organized, which one's the top, which one's the bottom. That's what this is. Okay. All right. So any questions on this before we compute the heat transfer?
I had a quick one. So does the thickness of the walls or the material affect the transfer?
Yeah, that's a great question. So if we were considering conduction through the duct as well, then yes, then the thickness would matter. But in this case, we're just interested in the convection, and so we're not going to concern ourselves with that thickness. But if we wanted to see how much heat transfer is going to the outside of this duct, then we'd have to pass through a conduction layer too. And so in that case, we would be concerned with the thickness.
Okay, that makes sense.
Mm-hmm. All right. And so now let's go ahead and put this all together and compute the heat transfer. And so the heat transfer, let's do it on the vertical plates first. So because now that we have H, we can just use our Newton's law of cooling, right? And so our Q is just going to be H1 times A times Ts minus T infinity, okay? Where A in this case, A is just going to be our H times W, okay? Which is 0.3 meters, which is H. And our W here is 1 meter, right? And so from each of the vertical plates, we're going to have a heat transfer rate of 43.02 watts. Okay. And then we're going to multiply this by 2 for each of the vertical walls, since we have 2 of these. Okay. Okay. So we'll do that a bit later. Okay. All right, and so now let's do the top plate. Okay. And so Q here is going to be H top times the area times Ts minus T infinity. Okay. And so we plug in for that. Then what we get from this is 47.025 watts. Right, then we have the bottom plate where it's going to be the same thing. So we have Q is equal to H bot times the area times Ts minus T infinity. Right. And then from this we get 138.6 watts. Okay. All right. And so the total Q here is just going to be the sum of all of these guys. Taking in mind, we're going to multiply the vertical one by 2. Okay. And so we add all that together and we get 271.67 watts. Right. And so that's the amount of heat transfer that we see from this duct, from the duct to the fluid. All right. So any final questions on this example here before we move on to heat exchangers?
You added the vertical, the top and the bottom together, or just the top and the bottom?
I added all 3 of them together, and so I did basically vertical 1 times 2 because we had two vertical surfaces plus the top one plus the bottom one. Yeah.
Got you. Okay, just making sure. Thank you.
Mm-hmm. All right. So that's free convection, and so free convection, it's for practically speaking, it's not the most you're not going to get high values of heat transfer from free convection, just because a lot of times if you add a fan or you add some kind of wind current there, any kind of forced convection, that's usually going to dominate in most cases. But it's an interesting phenomenon, and so it's interesting that you can get convection heat transfer without you explicitly doing anything to it. And so just by nature of having just density differences within the fluid, which naturally happen because you're heating the fluid and you're kind of affecting its density, you're gonna have some convection heat transfer. Okay. All right. And so we're going to move on from free convection, which I think is more of a cool thing and less of a practical thing, to heat exchangers, where I think this is probably one of the more practical topics that we're going to cover in this class. And so, first thing I'll say is that, just because heat exchangers, I'll be writing that word a lot over the next week. I usually like to abbreviate it with this. Okay. And so it's not hex. So I'm not casting a spell here, but it stands for, you can think of it as an HEX, which is heat exchangers. Okay. And so first let's define heat exchanger. So what does that mean, right? And so heat exchanger is a specific type of engineering device or engineering design where heat is exchanged between 2 fluids at different temperatures. Okay? Okay. And so kind of like a simplistic drawing of a heat exchanger kind of looks like the following, right? And so it's most of the time, we're going to consider two internal flows, right? And so let's say that, we have two pipes here and they're separated by a wall in between. And so we have fluid 1 up here. And on the bottom here, we have fluid 2. Okay. And both of these fluids are going to be moving. And so let's say that fluid 1 is going that way and fluid 2 is going this way. Okay. Question? So yeah, HX is 1 letter shorter. Yep, that's that's good too. Yeah, any time you can shorten these, it's always good. So yeah, anytime you see HEX or HX, that's usually means some kind of heat exchanger. All right. And so these fluids, even though I've labeled them as fluid 1 and fluid 2, they don't necessarily have to be different types of fluids. And so you can have water and oil, you can have water and water, you can have oil and oil, and so exactly what the fluids are, it doesn't matter too much. What matters though is that they're at different temperatures, right? And if they're at different temperatures, then we know that we're going to have some heat that goes in between them, right? And so let's say, for instance, that fluid 2 is hotter than fluid 1, then we're going to have heat that goes from fluid 2 to fluid 1, okay? Right? And so this is a very common device that very common design that you'll see in fluids. Or any kind of thermal device. And so you see these all the time in like an automotive engine. You see this all the time in HVAC systems, power plants, chemical plants. Even for like computer cooling as well, right? And so it's very common that if you're designing some kind of engineering device or any kind of engineering structure, you're going to have some fluid where you either need to cool it down or you need to heat it up in some way. And just the most efficient way to do that is just to run another fluid right next to it and have them exchange heat that way. Okay. And so, since it's such a common thing that you see in engineering designs, we're gonna devote a whole week to it where we study these kinds of heat exchangers. Okay. And so let's first let's talk about just some common applications. I just mentioned them out loud, but let's go ahead and write it down. Right. So common applications of heat exchangers, first of all, could be like air conditioning or refrigeration. Okay. 2 is the radiators inside your cars. Right. 3 is very common in like power plants or chemical plants. Right. And 4, and this list isn't all encompassing, but this is kind of the more common ones. It's also used in computer liquid cooling systems. Okay. And so it's used, everywhere. Okay. And so basically, in order to have a heat exchanger, you need to have 2 different fluids, right? And between those fluids, they're going to flow next to each other, and they're going to exchange heat. Okay. And so one fluid is obviously going to cool down, and the other fluid is going to heat up, right? And then that's usually something that's important for your design. Okay. All right. So any questions on heat exchangers so far? Okay. All right. So let's go over some types of heat exchangers. Okay. Because there's lots of different designs for heat exchangers out there. Just because there's lots of different applications. All right. And so the first one or first let's go ahead and talk about how heat exchangers are classified, right? And so heat exchangers, there's two ways that we can classify them. And so the first way that we classify them is by the flow arrangement. And so we'll talk about what that means in just a second. Okay. And then they're also classified by construction geometry. Right. And so first, let's go over the a very common type of construction geometry, and the one that we're going to use for the majority of this this week. Or this unit, because it's simple. It's the concentric tube heat exchanger. And so, if you've seen the word concentric before, what that basically means is basically we're going to have a tube inside another tube. Okay. And so from the outside, it might look something like this, right? So you're going to have an inner tube. And you might have flow that's going on the inner tube. And then you have another bigger tube that goes around that. Okay. Right. And so, each of the tubes here is going to have fluid that's going through it. And so for the inner tube, we have flow maybe going this way. Okay. And then for the outer tube, we're going to have flow going in the annulus that's around it. Okay. And so we have basically kind of, the inner tube is going to wrap around, or the outer tube is going to wrap around the inner tube. And so we have, basically kind of perfect coverage of, the surface kind of in between there. Okay. And so what you'll see me draw a lot in this unit is kind of the cross-sectional view of this. And so if we kind of take this and we kind of slice it across the center, it's going to look like this. And so this right here, this is going to be the wall that's in between them. Okay, so let me go ahead and mark that with red here. Okay. And we'll call this one in here the inner flow. Okay. And then on the outside here, we'll call this the outer flow. And you can see that it goes on both sides of the inner tube, right? Because it's, the outer tube is kind of wrapping all the way around it. Right. So this is the geometry we're going to be working with most of the time, just because it's relatively the simplest, and you kind of have perfect. You can think of it as like almost perfect contact between the two fluids, because the pipe that holds the inner fluid is basically completely wrapped around by the outer one, right? And so we have basically no heat loss, or virtually no heat loss, from the inner tube that doesn't go to the outer tube. Right? So any heat that's exchanged, or any heat that's lost or gained from the inner tube, has to go to or come from the outer tube, right? So we kind of have perfect coverage, and that usually makes our analysis, pretty simple here. Okay. All right. So this is kind of the most common type of construction geometry that we'll talk about. Right. And so let's talk about flow arrangement. Right? And so when you're talking about flow arrangement, what I mean by that is I'm talking about the directions of the flow, right? And so let's say that we have the case where we have the inner flow goes from left to right. Right? And so that's denoted by the arrows. If we design the heat exchanger such that the outer flow also goes from left to right, then this is what's called a parallel flow heat exchanger. Okay. And so, here we have, fluid going, the outer fluid's going the same direction as the inner one, right? And believe it or not, which direction that you flow the fluid has a big impact on its performance and how it actually, how we do the calculations, okay? And so parallel flow means they're going in the same way. Okay? But you can also have a situation where they flow in opposite directions. Right? And so let's consider a case where, you know, the outer fluid goes from right to left. Okay. Oops. What the? Sorry, technical difficulties. Okay. Right. And so if the outer flow goes from right to left, this is what's called a counterflow heat exchanger. Okay. And this has separate properties as well that you know, that we'll talk about later on. Okay. But you know, those are basically the two types of you know, flow configurations that we can have, or at least the ones that we'll consider in this class, which is parallel flow and counterflow. Okay. All right. So any questions on this so far? Okay. And so let's go over a couple more construction geometries that you might see in practice. And so another one that we can have here is called the cross-flow heat exchanger. Okay. And so visually it looks something like this, right? And so here we have kind of a bank of cylinders. Okay. Let me draw it like this, actually. Let me see. Okay. And so we have basically a bank of cylinders that's being kind of fitted together with a kind of rectangular slot. Okay. And you can see here that, you know, we're going to have several different slots here. Okay. And so these pipes kind of go all the way through. Okay. And each of those pipes, you can imagine, is carrying some kind of fluid through it. Okay. And then in between the slats here, and basically across the cross section of the across the outer surface of these tubes, we're going to flow a different fluid on top. Okay. Right. And so this is what's known as a cross-flow heat exchanger, because if you kind of remember from our section on external convection, this is basically that same situation where we have a cylinder in cross-flow here. Right. Right. So that's another common one that you'll see in practice. And I'll just go over just one more. And so one more common construction geometry that you'll find is a shell and tube heat exchanger. Okay. And so I'm going to butcher this drawing, guaranteed. Okay. And so basically this is a heat exchanger where, you know, you have your inner fluid, your inner tube is kind of coiled in a, you know, inside on the inside. And then outside of that, you have another, you know, the outer fluid, which is going to be, you know, kind of forms a shell around this tube here, right? So hence the name shell and tube. All right. And so on the inner flow, we have basically a pipe that kind of coils around like this. And so that's a terrible drawing, but you can imagine that, you know, you have a tube that is coiled on the inside. Okay. And so you have one fluid that goes kind of in this inner pipe that goes like that. And so that's normally like, you know, like some kind of liquid. Right. And then from inside the shell, you know, we have flow that goes kind of around this this tube like this, right? So maybe air is going to come in through the outside here. It's going to flow out that way. And so you have your second fluid here is going to flow through the shell of your of the heat exchanger. And typically, you know, because of the design, that outer fluid is typically some kind of gas, so like air or something like that. Just because, you know, it's a little bit easier to maintain that way. Okay. And so, you know, we're not going to analyze specifically these types of heat exchangers, but, you know, I just want to make you aware that they're out there. And so for, you know, for all of this unit, we're just going to focus on the concentric tube heat exchangers, you know, that we kind of, you know, talked about on the previous page. Okay. All right, any questions on this? Okay. All right, and so before we move forward, let's state some assumptions that we have to make. Because in reality, you know, a heat exchanger is a fairly complex device, and so in order for us to do our analysis in the class, we have to make some assumptions just to kind of make things a little bit easier for us. All right. And so first assumption that we're gonna make is we need to assume that any heat transfer from the outer tube only goes to the inner tube, right? And so in other words, any heat transfer from the outer tube to the surroundings is negligible. Or in other words, you know, another way to say this is that any heat that either goes into the outer fluid or out of it has to go to the inner fluid, right? And so it's basically we're considering as a closed system. Right. And so that's a big assumption for us because that's a lot of our analysis is going to hinge on the fact that, you know, any heat that's exchanges or any heat that travels is only going to be between the inner fluid and the outer one. Okay. All right. And our second assumption here, which is pretty reasonable, is we are going to assume no thermal generation. And so we're not going to have any heaters or any kind of, you know, radioactive fluids or anything like that. And so we just have just plain vanilla, fluids and gases that, that we're going to be working with. And so there's going to be no heat that's generated. And so we just have an exchange of heat between the two different fluids. And, you know, we're treating that just as a closed system, you know, just from that. Okay. All right. And so now that we have the assumptions out of the way, let's quantify how much heat would be exchanged just in a single pipe. Okay? Okay. And this harkens back to before the spring break when we were talking about internal flows, right? And so when we were talking about internal flows, the way that we quantify the amount of heat that's exchanged within an internal fluid is by a difference in the mean temperatures. Okay? And so for a single pipe, you know, we have the following relationship. We have Q convection is equal to m dot Cp times Tm O minus Tmi. Where TMO right here, this is the mean temperature at the outlet of the pipe. Okay. And TMI here, this is mean temperature at the inlet. Okay. right? And so if we take the difference between these mean temperatures, we multiply it by m dot, which is the mass flow rate, and we multiply it by Cp, which is the thermal capacity, then we can get the total amount of heat transfers that occurs. Okay. And so for heat exchangers, we have two fluids that that we have going on here. Okay. And so we can write out this expression for both of those fluids, okay, which I'll do on the next page. But before we do that, are there any questions on this? Okay. All right, so for heat exchangers, can write this for both fluids. I'm going to classify the two fluids as one fluid is going to be hot and the other fluid is going to be cold. Okay. Oh, sure. Okay. Great. All right, so I'm going to write that same equation, one for the hot fluid and one for the cold one. Right. And so which one's the inner fluid, which one's the outer fluid? It doesn't really matter all too much, since we're considering this as a closed system. And so what's going to be a better distinction is going to be which one's hot and which one's cold. Okay. And so for the hot fluid, we have Q is equal to m dot, and I'll call it H, okay, times CPH times THI minus THO, okay? And for the cold fluid, we can do the same thing. Okay? And so Q is going to be m dot C times CPC times TCI minus TCO, okay? Right. And, because of our first assumption on the previous page, which says that, this is a closed system, these two Qs have to be the same, right? And so any heat that's lost from the hot fluid has to be exactly the same as the heat that's gained from the cold fluid. Okay? Right? All right. And so if you can measure all these things, and so if you know the mass flow rate and the the inlet and outlet temperatures, right? Then you can, and kind of the properties of your fluid, you can compute the heat transfer, the amount of heat exchange just like that, right? And you only need this for one of the fluids. Right. And so one thing I'll note here, because things are about to get a little bit I would say not tricky, but kind of a little bit hard to keep track of. It's always good to kind of think about conceptually what's going on, right? And so I've characterized these as the hot fluid and the cold fluid, right? And so since heat is going to be exchanged between these guys, we know that the hot fluid is going to start out hot and then it's going to cool down, right? Okay. Right. And so knowing that, what that means is that THI, okay, and so the inlet temperature of the hot fluid, this is always going to be greater than the outlet temperature of the hot fluid. Okay. Right? Because the hot fluid has to cool down, right? And so it's going to start at one temperature, and then it has to cool down to some other one from the heat exchanger. Okay. And then by the similar token, the cold fluid is going to heat up. Okay. And so what this means is that TCO, this is always going to be greater than TCI, right? Because the cold fluid, just by nature of receiving heat from the hot fluid, it has to increase its temperature, right? And so the outlet temperature of the cold stream is always going to be greater than the inlet temperature of the cold stream. Okay. All right. So we got 1 more minute left. So any final questions on this? Okay. Right, so I don't really want to move on to the next thing until next week, but the next thing that we're going to go over in this lecture notes is parallel flow heat exchangers, right? And so we'll really get into, if you have a parallel flow heat exchanger, how do we quantify, the amount of heat that's exchanged? How do we quantify its performance? What situations is it good in? And what are some trends in the temperatures and the heat transfers that we can experience, that we can expect? Okay. All right, so that's all we got time for this week. So thank you guys for tuning in. And so remember, homework 5 is due on Monday, and so definitely, hopefully you guys are working on that. And if you have any questions on that, definitely let me know. So I have office hours tomorrow, but if not, you can email me or Discord me or anything like that. Right? All right, so have a great weekend, everyone. Thanks again for tuning in. Enjoy the rest of the afternoon, and I'll see you on Monday.
Professor, I had a quick question. Are
Sure.
you going to be putting these recent notes online?
They should be online, I think. Let me double check, but if they're not, then they will be very soon. Yes.
Okay, yeah. On mine, it doesn't show it.
Okay. It should be on week 11, so I have it on here. So it says a heat exchangers lecture notes.
Oh, I think I went to the one after for week 12. That's my bad.
Okay, yeah, it should be on week 11. Mm-hmm.
Okay, all right, thank you.
Yep. Mm-hmm.
Thank you, Professor.
Thanks, guys. Hamad, did you have any other questions that you want to ask? Okay, all right. And so if you have any other questions, you can just shoot me an email. But if not, have a good weekend.